Hello everyone. Today we are going to discuss about TOPAS, that is tool for particle simulation. So we are going to see the capabilities of TOPAS, what it can do with us, what is already done, and how you can use it for your usage. I have included one example to show how can you define your own input file, how your code is organized, how you can use it for your simulation. So let's get started. So basically, now talking about the capabilities of TOPAS, it is fully multi-threaded and support 4D simulation. That is, it can be used in parallel processing. That is, you can use multiple cores available on your system for your simulation, to reduce your computational time, and it supports 4D simulation. That means it supports the time as the fourth dimension, and you can do simulations for your gating treatments and like breath hold technique simulations that can be performed using TOPAS. Now you can also simulate the external beam treatment units such as proton beam, photon beam therapy units. You can simulate brachytherapy units. You can simulate depression treatment plans for your research purposes. You can also perform simulations on micro and nano dosimetry, that is simulating S values for cellular models, and doing simulation for radiolysis of water, that is radiochemistry, and you can simulate G value for radiolysis of water, direct double strand breaks, single strand breaks, that is direct and indirect effects simulations can be performed. It supports various kinds of variance reduction techniques that you can use for your simulation purposes. These are some examples of the simulation, the treatment units, or particle beam transport systems simulated using TOPAS. First is the IBA proton beam therapy unit available at the Massachusetts General Hospital, provided by IBA, simulated by the TOPAS developers. And below is another proton beam transport system simulated available at UC San Francisco, simulated by the TOPAS developers. And this is the front nozzle of the IBA proton beam therapy unit available at Massachusetts. And as you can see, the purple is the proton beam, the red one are the electrons, and the green one represents the photons, and these are getting transported throughout the nozzle. So you can visualize your transport of radiation in a similar way and do your simulation as per your requirements. These are this example shows the chromatin fiber placed inside a spherical world volume that we have done recently. In this we were trying to simulate the direct and indirect effects simulated by radiation, so you can perform similar simulations, and it takes TOPAS easily handle it. So as you can see, the radius of the sphere is around 50 nanometer, and it can go this small volumes. And this slide shows the results in terms of G value calculated for the radiolysis of water using TOPAS and Bio, starting from 1 picoseconds to 1 picosecond or 10 is power minus 6, 1 picosecond to 10 is power 6 microsecond, or you can say 10 is power minus 6 microsecond to 1 microsecond, and this shows the different ions produced. And TOPAS perfectly simulates these kind of experiments, and you can try for your own research. Now coming to what do you need to use TOPAS. Basically you don't need any knowledge of programming language or such as C++ or any other language. All you need is the basic knowledge of Unix, that is how to use the terminal, how to make a directory, how to copy paste something, and how to set the environment variables in Linux platform or the Mac platform. So this is all you need, and you are ready to. And you should, of course, you should have a basic knowledge about radiation physics. You should know what you are dealing with and what results you are expecting, and then you are ready to use TOPAS. This slide shows the basic example of TOPAS that you get when you install TOPAS. It shows a very big box that is shown with boundaries, these boundaries, and placed inside a small box placed inside a very big box. And the very big box is termed generally as the world box or the world volume, and the inner is our experimental setup, whatever we want to consider for our simulation. So here if you see the parameters, so it says that it's a GE represents the geometry component, and then is my box. You can put any name, like whatever is your name or your university name or whatever project you are working. So instead of my box you can say my geometry or anything else, and then is type, it's defined, so you have to put the type. So therefore different geometries TOPAS provide different types. So for this it is TS box, for sphere it will be TS sphere. So similarly you have to look at the manual and use the right type, and then based on the right type there will be the parameters. Like here for box we have to define TS box, we have to define the material, and if it is not the parent, then what is the parent to this box. So in this case it's the world, and the material is air. Then we have to define for like for box we know it has x, y and z dimension, so it is half x, half y and half z dimension. Here we have in the example it is given 2.5 for x, 2 meter for y and 1 meter for z direction. Then comes as how we want to translate our geometry, whether we want to move in x, y, z, and do we want to rotate. Basically this translation and rotation occurs with respect to the world volume, that is our bigger box. The origin of the bigger box is the real origin of your geometry or your setup, and based on that the changes occur. So in this case we are making translation in x-axis by 2 meters, and we are not doing any rotation or translation in y or z direction. So this is the thing. And now we see this these as these are basically the data types. These are just to put a double check, because in case you put put it here double and then you put true here, that means you are using boolean, but here you say it should be double, so it will be conflicting, and TOPAS will instantly check and let you know about your mistake. For example, here it's string and you use 2 or any double number, then TOPAS will instantly let you know that you are doing something wrong, please check. So this is the way you can TOPAS helps you in definition of your geometry. Then the second thing you need for any simulation is your transport parameters, physics transport parameters. So there are many models available in TOPAS that can be used. but for simple geometries and simple testing, you can use this kind of thing. SV means the string vector, and physics, you have to use it like this. It means you are using physics parameter, and then you can put anything here. Let's we are saying default param modules because it's the default, and we are using the name module. Which one? We are using the one module, that is G4EM standard opt4 module. So after the physics parameter, there is a parameter for graphical user interface. So it starts with GR, and then you can name whatever you want to put. Like I put name view A, you can put view B, view C, view D, or whatever you want to put, or graphical user, whatever. Then here also you define the type, then the window X, Y, include X's or not, what how you want to rotate the view, that is decided by theta and phi, whether you want to provide projection, perspective angle, zoom or not. Here I use the zoom 2, and pause before quit is generally it's a TOPAS parameter is generally to represent like when you run your simulation, whether you want to stop, freeze the view, or maintain the view open, graphical user interface view, or you want to close it as soon as the simulation finishes. So if you keep it true, so it will pause and it will not quit instantly, and it will quit only when you want it to quit. Otherwise it will automatically quit, and you have to that's your choice, and you can do whatever you like with your simulation. Now how you define now is how your simulation run when you run any simulation, how it looks. So basically, like in this example, the name was openbox.txt. So when you run this simulation, this your front terminal will appear like this. So it shows basically it shows that welcome to TOPAS, the version of TOPAS, what type of license do you have, and where it is registered, and how you can register yourself. So you can go to topasmc.org registration, and you can register and get your license. And it says that every user must have their own individual valid license to use TOPAS. And then it shows what is the file we are using. It is openbox.txt, and then it shows where is our environment variable set for ginfo data, that is G4 data. So it shows, and then which version of ginfo data is used in this. So it shows and which mode it is. It's multi-threaded mode. Then it talks about the user interface, and in this one we are using only one thread. And then it talks about the world size and tolerances, so surface tolerance, radial tolerance, and then it checking the unused components, and it performs some checking. And then these are the parameters for visualization. And since there was no history, so it says history 0 or TOPAS run complete, and pausing at G4 so similarly you can see there is pause for quit is true, and if you want to exit, you just write exit, and it will finish the simulation. Now if we see how your TOPAS application is organized, so basically TOPAS is developed over G4 simulation toolkit, and the G4 simulation toolkit uses G4 data files. So when we install TOPAS, we use these data files. These data files are are attached with the TOPAS application, and then the simulation is performed. These data files include the standard GN4 physics cross-section data files, and the TOPAS application is, as I mentioned before, is built on GN4, so you don't have to separately install GN4 software toolkit, and it is already included in TOPAS application. All you have to do is you have to provide your parameter files. It can be a single parameter file, or it can have multiple files, if you have, for example, for any simulation, you need the geometry, you need the source file, source type or radiation source type you want to use, and then how you want to score them, and what should be your physics parameter, and whether you want to use a graphical user interface or not. Based on that, you can have you can put all of them in separate files. Here in this presentation, whatever I am presenting is all are included in single file, but it is recommended, or you can use it to put in separate file. It saves you from making errors and make things little separate and easy to handle. As I mentioned, TOPAS parameter file includes geometry, particle source, physics parameters, or the model we are going to use, how we want to do the scoring, and whether we want to use the graphical user interface or not, and then what kind of time feature we want to use, or do we want to use a time feature or not. That is all your choice, and depending on that you can do use it for your application. So more information on the parameter control can be found on the website of TOPAS, and it shows how it is designed, how you have to write your syntax for your input file, how many statements can be given in a single line. So this kind of related parameters, what happens when we have 4 or 5 or more than one input file in the text format, and then joining them together, how they behave, is all presented here. So to understand the TOPAS parameter file, I prefer to use an example. So in this presentation, I chose to estimate the radial energy deposited along the radius of this sphere when we put a radioactive point isotropic source of hafnium-166 at the center of the sphere. So this is what I have estimated or simulated using TOPAS. So we expect to get similar energy distribution. So as the radius increases, there is decrease in energy deposition, and the maximum energy is deposited near the source and minimum far from the source. So we expect to simulate the similar thing using TOPAS parameters. So let's start and see how we can do it with TOPAS. So for our simulation, we have considered hafnium-166 isotropic point radioactive source. Radius of the sphere is going to be 1.2 times of the CSD range of the emitted electron with maximum energy. We are going to place our detector, that is our sphere, that is of 1.2 times the CSD range, into a much larger sphere that we are going to call the world, and then we are going to divide the sphere into 28 shells, and basically we are going to score energy in these 28 shells in terms of mean energy deposited, total energy deposited, and the standard deviation. So the maximum energy emitted, electron energy emitted by hafnium-166 is 1.854 mega electron volt. CSD range for such electron is 0.89 centimeter. If you calculate 1.2 times of CSD range, it is going to be 1.079242 centimeter. And this is the geometry that I described before. So we are going to put our shells in a very big sphere, and these shells are these 28 shells with it has minimum radius and maximum radius, and in between minimum and maximum lies the medium radius. But however, in these calculations we are not going to use the medium radius. So in case you want to know, then you can estimate the medium radius. It's nothing but just half of middle of minimum and maximum. So we divided the whole 1.2 times CSD range into 28 values, and based on that we get the minimum and maximum radius. So we are going to use this, and we are going to design our geometry setup, then we are going to define our physics setting, and then we are going to define our source, and finally the scoring and the graphical, how we can do it. Let's see. So before defining our spheres, we need to define our world volume in which we want to put our whole geometry or the experimental setup. So I have already discussed this. D and S. D means double, B means boolean, and S means string. So any volume we define, we have to define its type. It's not given here, you have to define it. Then we have to, based on the type, there are some parameters defined to define that volume. Like for sphere you have to define radius, for box you have to define x, y and z dimension. Here we have to given half x, half y and half z dimensions. And finally we this is related to the visibility of the geometry in your simulation, or when you see open the graphical interface, whether you want to see your geometry, world geometry or not. And this is just the material of the geometry. Another thing to note is when you put a hash in front of any line, it is anything after that is everything after that is considered as comment, and you can put these lines statements in any sequence. You don't need to worry about whether to put x first or y first or z first, or put the visibility content first or the material first. So it's your choice and you can do as you wish. Finally, at the second stage we have to define our detector, that is the sphere and the shell. So basically we define a very big sphere that is of, as you see, it's 1.8 centimeter, and our 1.2 CSD range is 1.079. So this is almost double of the sphere. So basically to define our first sphere, the bigger sphere, we define the geometry component. I name it W sphere, you can name it anything. Then you have to define its type, whether it has a parent is defined for the daughter volume, so its parent is world. What's its material, we define this G for water, and we gave it the color blue. And you'll see, I'll show you in the at the end in the graphical interface section how this blue and red are different. And then you have to define the R minimum and R maximum. If you are defining simple sphere, you just have to put R minimum equal to 0, because it doesn't have an inner radius, it only has an outer radius of 1.8 centimeter. You can directly use same as 1.2 times of CSD range if you wish. You don't need to put this big of the external radius. Then this S5 and D5 parameters are generally used to provide the theta and phi angle to generate our sphere. You can vary them if in case you want to define hemisphere or a quarter part of the sphere. So this can be done using theta and phi parameters, and here also whether we want to see the geometry or not, so we put it false because we want to see the geometry. In case we don't want to see it, then we put it true. And similarly for the shell, we have given it the name W shell 1, and you can give it any name you like. And then is the type, parent, similar to that. Here we give color, and here you see we have defined R minimum and R maximum. These are the same values you can see of the R minimum and R maximum that we calculated here. You see 0.02955 and 0.0475. So it is the same thing. So you can do in this way. You can define the other shells and you can name them shell 1, shell 2, shell 3, or whatever you want to do. And not only boxes and spheres, TOPAS provides a wide range of geometries similar to GINT4. These information can be found in the user manual, as you can see, and it is the online manual of GINT4. It tells about the placement, parallel words, electromagnetic field, visualization attributes, dividable components, generic components, group components, specialized components, and patient components in case you want to define or simulate the patient treatment. And here also, as you can see, my component. So in this part, my component, you can put whatever name you want. You are free to use, but keep in mind that this S, G, geometry thing, and the parent, these things should be same in the same manner. Means you cannot change their name because they are already defined in TOPAS and they have a fixed meaning. So you cannot define your own until or unless you define your own extension with the different names or different things. Now comes to the physics settings. So for default physics, in case you are doing clinical simulations for the X-ray therapies, and the default settings are the modules that are suggested that you can use are these 6 modules. So see you observe how they're written. It is given string vector, then it's physics, then the default parameters and the name of the modules. There are 6 parameters, so they put 6, and then it's like G for standard option 4, G for H physics, Q, GSP big, HP decay, G for ion binary cascade. So it basically includes all the carbon, ion, proton, X-ray and electron physics models that you can use for your simulation. But not only this, these 6 are just the default models. In case you want to use any other physics model, then there are you can select any of the dozens of GN4 reference physics models from the GN4 physics reference physics list, or can build a GN4 modular physics list for yourself. So you are free to do. TOPAS supports nanoscale processes or similar, so you can use the physics list defined for GN4 DNA as well for faster physics, and for basic tests or examples you can use the GN4 EM standard option 0 of the physics list is given in TOPAS. Now comes the The source definition: TOPAS supports various type of sources, that is beam, emittance, isotropic, volumetric, and phase-space source. For this simulation, we are going to use the beam source. Let's see how we define for this example. So for this presentation, we consider isotropic point source, radioactive point source. It can be defined as follows. So it has many parameters. First is the type, then is the component, beam particle type, and then you define the beam energy spectrum type, and then energy values with unit, and then is the weight. So first of all you define the number, and then you put the values, and then if it's an angular distribution or position distribution, since it's none, so I put it none. And how many histories you want to run. Here we run for 5 million. And here also it has different data types given behind. So it is like a string. The type of source we want to use is isotropic, component is beam position, particle type, beam particle is electron. We want to use energy spectrum of type continuous. We have a double vector of beam energy values. There are 20 values, and the unit is MeV. Then we have since it's unsigned, it doesn't have any unit, so vector. So so it has weights, and there are 20 weights, and U is basically for the cases where we don't have the units, and that's it that you have to do to define your source. You might have the different position things like the conical source or any volumetric source. You can define in a similar way. And so more definition or more information on source definition can be found on the manual with the particle sources. It shows the parameterization, emittance, parameterization, isotropic, volumetric, and phase-space source options. There are beam sources, different type of sources available, and you can use it. And there are some custom particle sources available as well that you can use. So you can check the manual and use as per your preference. Now comes the final part, or is we want to do the scoring, or we want to measure whatever we have defined. We define the geometry and the physics. After that comes the measurement section. So TOPAS layer is built on the top of G4 multifunctional detector of G4, which basically helps to compute the dose, fluence, surface current, phase space, and many other quantities. So you can use them to score your the things based on your preference. For this work we define the score for each shell. Maybe you can use a different approach, but in our case we wanted the energy deposition in each and every shell. So what we did is we defined a score. So here we define the quantity, then the quantity is those two medium, then the component where we want to do it. So we want to do it in W shell 1, and then as what if the output file already exists, so we put override. Then output type is CSV. You can put XF format or the root format as well. Then output file name, and then what you want to report, it's the sum, that is total energy deposited, and the mean, that is particularly deposited in that shell, and the standard deviation in the calculation, and it also has different data types just to save you from errors and mistakes. So similarly you have to define for other shells as well, like shell 1, shell 2, shell 3 and till 28. So basically when you run the simulation you are going to get 28 output files that I'll show you after the finishing of this presentation, and then you can take these values, put them in a single file by a simple C++ MATLAB program, and do the analysis of your result whatever way you want. So more information on scoring can be found in the manual. It provides volume scorer, proton LED scorer, surface scorer, phase space scorer with different formats. You can filter your scoring, like you can calculate the dose deposited by the primary electrons, secondary electrons, or just photons. You can filter out such things. You can output in the specified outputs like DICOM output, DVH or histogram output, or the phase space output. You can do other form of scoring as well. TOPAS provide wide range of scorers for scoring purposes. Now finally coming to the graphical user interface, as we saw in the previous in the geometry description section, we gave blue color to our sphere and the red to our shells. So if you see the radius of the sphere is higher than the 1.2 times of the it's like around 1 centimeter, the 1.2 times of the CSD range, but we are giving 2 centimeter as radius, so it's going to be big, and so here it's visible. This is blue and all our shells are inside it, so as you can see. So here also you have to define the type, then the window size X, whether you want to translate the geometry or in X or Y, since it's a 2D view, whether you want to rotate the view by theta and phi, what type of projection you want to see, perspective angle, zoom, whether you want to zoom it or not, whether you want to include the particle tracks or not. If it is true, then you have to define color by the particle type, how you want to color the things, then is particle names, and then you have to define the type of colors. So hidden lines removal for trajectory, you can make it true or false, where basically is just to make the trajectory smooth, include the axis or not, what should be the axis component, like in all cases as I mentioned before, world is the axes are defined with respect to the world, then what should be the size of the axis. So this is how you can define the things, and based on what it takes, it has different data types related to it, as we saw in the previous sections. Similarly you can do for the geometrical interface. More you can find on the user manual of this TOPAS, and you can check what you can use and what you can not use, and how you can define your graphical user interface, and see your geometries and get beautiful pictures for your publication. Thank you. Now we see the output as I talked about. So this is my input file basically that I showed you before in the presentation. So basically it starts with the world geometry, then it shows the bigger whole sphere, and inside the whole sphere there is shell 1, shell 2, shell 3, 4, 5, 6, 7, 8. Similarly, these are all, I defined all the 28 shells, and after the shell definition comes the position of how we want to position the source, and the source is positioned at the center. So this is basically the positioning I missed in the presentation, but you can see we used the parent as a sphere, and type is group, so it is source to all the shells, and then we put the translation XYZ, so and rotation, so basically we are placing it at the origin. This is being positioned, then we define the source, then we define the physics energy cut, and the physics we are using the default setting, so we didn't provide any physics here. We just put the set production cut to 50 electron volts, and then we did the scoring those for all the scorers here. So it's defined for shell 1, shell 2, shell 4. Similarly for all shells we define, so it is defined for 28 shells, and then if you want to dump all the parameters, that is the physics list and other things that have been used, you can keep it true, otherwise you can put it false. Then how much histories you want to see on the screen after that to print, like if we are using 50 million, and so after 5 million it will print on the screen that this much has been already run, and then how many threads, as I mentioned, it can use parallel processing. So in this exact case we are using 4 cores, 4 threads, and then you can define your graphical user interface and provide, based on the angles theta and phi, you can define your different views and use for your visualization. Like here we used theta is equal to 45 degree, earlier we used only 0, so, and pause before quit, these are just basically related to your geometry. So as I mentioned here, there are 28 detectors, so 28 detectors will result in 28 output files. So you can see there are from S1, S2, S3 we have 28 output files. So if you see what is inside, you will see that there is a okay, so it says oh sorry, let's open it in text file, just gedit. So you can see it tells the TOPAS version, output file name, parameter file name, what it's scoring, so it scores the sum, mean, standard deviation. So this is given here. So in the similar way it is given for all the 28 detectors. You can get them out and put them on a single file, like I have done using some program. You can accumulate all the results in single file, and then you can do your data analysis. So this is how you can do your work and carry your things and do your simulation. I hope this presentation helped you to understand how you can design your application with TOPAS and do the simulation for your own experiment or your own research study. So thank you very much, and if you have any questions, please let me know.